class online. So I cannot hear the students because all of you are mute, but you are supposed to have the option to unmute. Can you unmute and then I'll see if I can hear you?
Hello.
Hello.
I don't hear the question from the student. I see that some people got unmute, like John.
Can you hear us?
No, let me change a second. Can you say something again?
Hello. How's your day been?
Okay, now everybody's on mute. Can someone say something?
Hello.
No,
Hello?
there's something wrong on my play because I don't hear any audio.
Can you guys hear this?
How can I do? Why? I
Hello?
cannot hear anyone.
Testing.
That's
Testing.
interesting. I already joined the audio. So I'm gonna disconnect and connect again, just in case. Stop share. Hello, hello. Do you hear me? Yes. Okay, I think I can hear the people now. Okay, now it's working fine. Let me reshare the screen. And then I'll record the lecture. I'll open the chat. Okay, so it was a problem of the audio playing. So now I can hear the questions and the participants. But what I'm gonna do is to not have a lot of noise, is to mute everybody but me. Okay. Yes. Okay, so welcome to class. Do you hear me now? Someone types yes, just to make sure. Yeah, okay, perfect. So in theory, I can hear you. You unmute. You should be able to unmute. If not, I can see the chat. If you post something on the chat, I can unmute if there is a problem. So welcome to class. So what are the announcements that we have? So as you might have seen the announcements, the in-person lectures have been canceled. Yeah, I don't know how to mute the doorbell. With such a large class, that's going to be interesting. So the classes are going to be online. That's going to be the link, but there's only 2 lectures. On the quizzes, it's going to be online. That's what we're having. It's at 2:50. We have the quiz. It's automatically power up. Now the quiz is slightly different. That now we have a pool of questions, and every student is going to have a different one. And the reason is because we're starting to test what's going to be for the final exam. So the final exam, we're going to do it on Canvas. So obviously you cannot collaborate on the open exam. It's individual and there is an honor code. But because it's going to be at home, it's going to be open book. It really doesn't matter so much if it's open book, closed book, but so to make it more fair, more simple, it's gonna be an open book exam. The lectures, I'm recording it with the let me make sure that I'm recording. Yeah, I'm recording with the Zoom, and so I'll be able to post the MP3 at the end of the later. Like I don't know how much time it takes to create the MP3. There is any question on the announcements? Yeah, the slides are in the Google Drive. The MP3 will be in the public drive. And the slides are already released in the Google Drive, so you should have them. Now, to get back the midterm 2, oh, I like this thing of seeing the chat to the questions. For the midterm 2, some people are asking, is the idea that Akash has the exams? I'm not so sure what is the status for this to get it back. If he cannot physically get them, or you can or don't want to go to campus, maybe there is a way to send some photographs of the exam and send it back. It's something to coordinate with Akash. So he's in charge of having the exams. Yeah, on the exams, it will be the final exam. It will be Canvas, so it means it's going to be a multiple question option, like what we have been doing with the quizzes. The only thing is going to be a little bit longer, so I can have options to fill a table, and then you all say it's table A, B, or C, so to get the results. In some places, I can ask for text, in which you can write text for what is the answer. So you have to compute CPI. I might ask you what's similar to the quizzes they have done in class, or I can ask you for text. The issue with text is it cannot be auto-graded or anything like that. It will be similar to the quizzes, but a little bit longer and more questions. Okay, I see another question there, so I don't miss them. Is still have office hours, so yeah, so we'll have like a 30 minutes break after the class, and then we'll have office hours. One thing I might do is I might record the lecture, the office hours, and then post them. I'm not so sure, depending how this thing works. Any other question? No. So on the final, it will be like the quizzes. So they will be randomized, and you will not be able to go backwards. So I see that someone has been asking this. So in the sense that to complicate a little bit the collaboration that is not supposed to happen, is that you cannot go backward on the questions, and the questions will be randomized. Not everybody will have the same questions. The time is not per question, it's per exam. And it will be a 2 hours, under 2 hours exam. So I still have not finished the questions. I start to think about them, but not because now it's switching to Canvas. So I don't have the time. You will see the time there. So the midterm grades, I thought they were already uploaded. The only issue is that they forgot to grade some of the DRCs. There was a mistake there, so have to upload the grades for all the DRCs. So that's the main issue with the grades. The students have the grades, but at the end, but it's there. Any other question? So there's one about partial credit. I'm assuming that this is for the quizzes, so for the midterm. There are going to be more questions. So it's not going to be 3 questions like we had before. Maybe there are like 8 or 10. So it's going to be each one of them. If it's text, you will have partial credit. If it's not text, there is no partial credit. It's slightly different than paper. Yes, you are not going to be able to go back. So there are issues with the midterm grade. I cannot check now, but the idea will be to check with the. Let me check after the class, because the TAs told me that they already have the grades. They have an issue with the DRCs, so maybe they didn't upload because of the issue with the DRCs. So for the lecture today, so the slides that we have today, I don't think I'm gonna finish, but if I finish is everything that we have for the final. So the idea is that we have 2 days to cover those slides. There is no more than the slides that we have today. So the material is multi-core. That's what is missing, but one thing that you have to be careful is that the book does not cover many of those things on the multi-core. So you really have to go over the slides. I don't think I'm going to finish all the slides. So after the slide set that I have today, that's the last set of material. But more likely I will have to finish on Thursday. So what is the thing we're going the last day? We're going over hierarchical page walk. This we already saw it. The idea on the hierarchical page walk is that we want to translate from a virtual address. Oops. We want to translate from a virtual address to a physical address. And then what we do is we divide the virtual address in several chunks. We have an offset that usually is 4 kilobytes. And then we have several index. So this can be the index 0, this can be the index 1, this can be the index 2. So you get the index 0 added to a starting register, find another table, then you get here, you add plus index 2, and then in this case there's only 2 levels, and at the end you have your page permissions. So you do the hierarchical translation. We already saw this, but it's a quick review. Now for speed reasons, doing that translation, it will be very slow. So what you do is you have a TLB that mostly is a cache who remembers the results from the last translation. So you need to translate from virtual to physical. And in theory, to do this translation, you have to do several loads to traverse. Instead of doing all these loads to traverse, you remember the translation. So it means that the first time you're going to go check on the TLB, you're going to have a miss because the tag will not match because nothing is there. Then you do the translation. Once you have the translation, you remember it. The next time that you go to the same page, so you have the 4 kilobyte page, the same one, it's going to be hitting on the TLB, so you remember the translation and you don't have to do the page walk. Now, one thing is that the page size tends to be variable size. Most CPUs support several sizes. So what happens is that the default, everybody has from 0 to 11 or 4 kilobyte pages. But if you think about it, if you have 4 kilobyte pages, you have an application that has 4 megabytes, which is not so many, you need 1,000 TLB entries. So that's a lot of performance overheads. So what is the thing that you have to do? Is you have the option to have maybe like 1 megabyte page size. So you have different page sizes. If you have a 1 megabyte page size, then it's not a problem to have a big amount of memory in your application. Now, how do you support this on the TLB? On the TLB, you have two offset size. Now, when you match the virtual page number, you're gonna do a check against the tag. Now, if the tag hits, then you have a hit. In the virtual page number, you're gonna have also information about the translation if I have a 4K page. So this is if I have a 4K BPN to PPN. And you remember if it was a long or a short page. So here I can have is 0 or 1. If I have 0, it means 4K page. If I have 1, it means 1 megabyte page. So when you do the translation, the index, you can reuse all the translation or you use directly the BPN. The reason for why you use the BPN is because if you are in the, you notice this part here, this is the same as the BPN, doesn't get translated in the 1 megabyte. Here's when you're going to have the PPN. Here's when you're going to have the PPN. So this part is what corresponds to this part. So what you can do is to do the translation of multiple page sizes inside the TLB. One thing I see that so there are some questions about the midterm. Let me see. There is, do you class it remotely? For the, some people are asking, how do I see my midterm 2 or 3? So that will be with the, you have to coordinate with Akash who has the midterms. He had to figure out how to share if you don't physically go to campus. He lives on campus, so he can physically share, but he doesn't want it or it's not available. Maybe he can set it on Zoom and then he can scan and send it to you. That's something to coordinate with Akash, which is the one who has the midterms. Anyway, any question, switching back to the questions here, any question on the TLB? So remember, the TLB translates from virtual to physical, and you need that for security and to simulate bigger memory. The main point of the TLB is that doing that translation, the page walk, is very costly, you have to do 2 or 3 loads, so you have to remember the translation, and that's what's the TLB. One little challenge on the TLB is that you have 2 page sizes or more. In this class we are going to do only powers of 2 pages, and it's always powers of 2. But you can have several page sizes to do the translation of the TLB. This is another picture how to see the same thing. Now on the TLB entry, so you have the most important fields are the physical page number. You're going to have permissions that is going to tell you, do I have read access, do I have execute access, do I have write access. Many systems have some other information, like is the page dirty. They have for statistics, like how frequently have you been accessing it. And the reason is because this thing allows the operating system to decide which page to move out in case that they want to do some decision. So there is some potentially information for statistics. But the important ones that you cannot avoid is the physical page number and the permissions. Now when we replace from the TLB, you have, it's like a cache in a way. So you can decide if it's fully associative, what do I do? Do I do LRU? Do I do MRU? How do I do? You can have a TLB that is direct map translation, which in this case there is no replacement policy, or there can be a 2-way associative TLB. It's the same syntax and naming that have been using on the caches. You can do the same for the TLB, but most of the time the TLB tend to be fully associative. Caches tend to be 2-way to 8-way associative typically, but TLBs tend to be fully associative. So this is just a little, the same thing I've been mentioned with a little more detail, how the translations can be. So you have the virtual page tag. So you have the physical page number. Now, one thing that here that is interesting, that is because it's a more realistic case, is that you have a process ID. So what is this process ID? This is an example from RISC-V, so it's more realistic example of how to do the TLB. Now, we have a process ID because look what happens if in a normal. You have a process 0, process 1, which is mean 2 applications. One is BI, another one is like chess game. So now you have the CPU, and both of them can run on the CPU. The operating system might be running one, and then it does a context switch and switches to the other one. Everything that you have on the TLB, it has to be removed, because otherwise I will translate from my BPN 0 to physical page number. So, or I will translate from my BPN 1 to the same physical. When I switch from process 0 to process 1, I have to change the translation from here to here. So it means that everything that I have on the TLB has to go. So it means that whenever I do a context switch, or I do a system call, I have to destroy my TLB. So all the entries have to be invalidated. That can be very costly, and most CPUs, what they do is that they have a process ID that is managed by the operating system. And if the process ID is the same, if it's different, it doesn't need to flash the TLB entries. So that's like a performance optimization. Which brings what is the issue with the TLB? When you switch between context processes, unless you have a PID, the operating system must flash the entries in the TLB. And the reason is because otherwise one TLB will access the other, one process will access the other process data. The alternative is to have a PID. Sometimes they call it ASID, or address space identifier. So this is the same. It's only that I tend to have different names depending on the ISA. And in that case, you can have multiple processes or multiple programs coexisting on the same TLB. Now, the thing that gets a little bit tricky, and it's easy to understand that there is a potential problem, is now I have caches who remember values based on addresses, and I have TLBs who translate from virtual to physical. How do I mix these two things together? The obvious case is to have virtual caches, and that's what they were doing the first systems that they were in the 80s. So what does it work on the virtual cache? So you have your CPU, you have your L1 instruction cache, L1 data cache, and then you might have your L2 cache, it doesn't matter. All those ones are working with virtual addresses. Only when you have a L2 cache miss, you translate from virtual to physical. Instead of doing an L2, you could do it in the middle, after L1 miss. That doesn't matter so much. So after you do the translation, here is physical addresses. You're going to have to do the translation before going to memory, because otherwise it means that you have no TLB. Now, what is the advantage thing of this? Is that all those caches are unchanged, so there is no overhead for the TLB. Now, because the TLB is used very infrequently, only when we have an L2 cache miss, it can be big and slow. So all those things are great, but there is most current CPUs don't do this, and there is a reason. And the reason is that it requires a cache flash on context switch. Notice that here we have a virtual address. If I switch from process 0 to process 1, this virtual address are going to be conceptually different. But here so for example, this one in address 100 might have a secret key. This one is not able to access that address 100. But if I context switch, suddenly it might be on the cache, on the data cache. So by doing a load, I might be able to get the data from the other process. So that's an obvious security problem. It's not allowed. So what you have to do is to flash the contents on the cache. So which means that you have to write back and invalidate the L1 and L2 caches every time that you do a context switch. If doing a TLB translation, if doing a context switch on the operating system was requiring a flashing of the TLB, and that was costly because we have a PID, imagine how costly it is to flash structures like this that it can be like 1 megabyte. Or this can be 32 kilobytes. So this is going to be a very slow process. So the issue here is this works great if you do infrequent context switch or system calls. The majority of the systems don't do that. So what can you do that it's a little bit simpler? And this is, for example, what previous AMD CPUs used to do. Before going to the caches, I do the translation. So the CPU is going to send a load. Before sending the load, I do the translation, and then the caches only see the virtual address, the physical address. The caches don't need to be flashed or invalidate. There is no sharing problem. Now, what is the problem? Is this thing, adds one extra cycle. I have to do the translation before going to the cache. And we know that the APMAT is the time hit plus the miss rate multiplied by the time penalty. This is adding at least one cycle to the time hit, which is not great. Also makes the TLB to be very small in order to cycle in one cycle. So what is the solution that nearly every CPU is doing nowadays? Is to do virtual index, physically check. So in the cache, we have the tag and the data. So in parallel, we are going to access the TLB. So when we have a virtual address, we're going to send it here, we're going to send it here, we're going to send it here. Now on the tag, we are going to have a comparator to decide if we have a hit or a miss. And we also have a valid bit here that we are saying it will be hit only if these two things are true. Now the thing that is different, that before we are connecting here, so that's not what we do. In fact, let me just put a different color. What we do, we get the result from the TLB. So here we have the physical address. Here we have the virtual address. So we check the TLB in parallel we check out the tag. And then when we compare is the physical address of the translation. If we have a hit on the physical address, we have a hit. Now the advantage of this system is that it doesn't add extra delay. It's a little more difficult to design. It has to say the virtual address has to go to 3 blocks. And there is a potential issue. This is the virtual address. This is the physical address. If we have a 4K, that is the typical. So here, just to make sure that we understand that it can be different sizes. So here we have offset. Here we'll have BPN, here PPN. Now to index the Xbank, how do we select the index on the cache? So we are going to index with the virtual, no? So what do we have to do? We're going to have an offset, we have an index, and we have a tag. That conceptually is going to be overlapped here in some way. Like the offset is going to be much smaller than the page, and then the index, let's assume that it's here, and then it's the tag. So we have tag, index, offset. If we have this thing, that's okay, because you notice when we compare the address, that is the result from here. The index that we have used, the virtual index is equal to the physical index. because these bits don't change. But notice what happens if I have a very big cache here. So let me change the color. If I have big cache, and this is my index, this is my offset, and this is my tag, the virtual index is different than the physical index. Because it's different, when I index in this tag, it can give me a different result. As a result, in this class, there are some solutions, but they are very difficult. The index that you use for selecting on the cache cannot be beyond the page size. If I have a page size of 12 bits, which is the same as saying 4K byte page, it means that the index on the index for the cache, this thing, has to finish before the bit 11. If you finish before bit 11, you cannot do this design that is a virtual index physically check cache. Any question on this? Let's have a mini break. See if there is any question. I can go over questions on Canvas. No, on Canvas, no, sorry, on the chat on Zoom. The question is, what's a page? The page is when you translate from virtual address to physical address. If I go back to the recordings, so it was here. So I'm translating from this virtual address to this physical address. The page is this size, it's the offset that you can have. Usually it's 4 kilobyte page in most operating systems, but technically you can have any page size. So page is the same as saying cache line for, it looks like the cache line, but for virtual memory, for the virtual to physical address translation. In a CPU, in the caches, we tend to call it cache line. In the virtual translation, the lower part that it gets untouched is the page size. Now there is let's see, what's the next question? Is the lecture recorded? Yes. Is today's quiz on virtual memory? No, because we are still covering virtual memory. I always ask about questions on the past. What is good sharing? I'm not so sure what you mean by good sharing. I don't know, when did I say good sharing? Someone is asking about good sharing. The lecture is recorded and I'll post it, but it will be on the drive. The reason is that it's going to be on the drive is because the room might be recorded, but it will be empty. No one is there. Can we go over quiz 8? Yes, we can go over quiz 8. I forgot about what was quiz 8, but let me try to find it. Okay, so quiz 8. No, quiz. I don't have it in the quizzes. Quiz 8. I'm checking the quiz questions. Okay, so quiz 8, for whatever reason, I don't have it on my PowerPoint, but the question, Funny, it doesn't let me see the quiz. It's kind of. Okay, so let me share the other screen. So then we'll be able to see the quiz thing. Okay, I think we are sharing the quiz now. Let me put the chat again because for whatever reason the chat disappeared. So what is the thing we are seeing on the quiz? This is the first question, and I see that most of the people got it correctly. It was, we have a direct map cache with 256 byte cache line and 16 byte offset. Notice that I tend to give, for many questions, easy powers of 2, that it will align to the hexadecimal, like multiples of 4. But anyway, here it doesn't matter. 256 bytes cache line, a direct map, and 60 bytes. So on this one, it's a direct map cache with 256 cache lines. So there's a total of 256 cache lines. How many are 256? It's 2 to the 8. So because it's direct map, we know that the index has to be 8. So it has to be one of these 3. Now the cache line is 16 bytes each. So it means that the offset has to be 4. So now it has to be one of these 2. Now the CPU is a RISC-V 64-bit, so it means that the virtual address or the address is 64-bit, which means that it has to be 64 minus the 8 minus 4, that is what you are using, and that's what's going to be the 12. And most of the people got the answer here correctly. Now, on the second question, it's a slight variation on this one. There was more disagreement on the size, but we have a two-way set associative cache with 32 kilobytes, or 2 to the 15, and 64 bytes, or 2 to the 6. But this time it's an RB32. Now, how many bits are in the tag array? Now, the first part will be to figure out how many tags do we have. So here it will be the 32,000 divided by 64 is the number of cache lines that we have, and that's 512. So we have 512 tags, because the associativity doesn't change the number of tags that we have. So here you're going to have 512 or 512, and then you have 32 bits ISA, you have 32, and then so it will be between this or this, because whether you have 14 bits that you have to remove, that is the index size. And why it's 14 instead of 15? Because it's a two-way associative. And then you have 1 bit that is for the valid and 1 bit that is for the dirty. So this is what you have for this answer. Any question? I would see that there was a bunch of questions, but I don't know if they're quiz related. So cache lines, what is the dirty bit? Remember, let me switch to the other one so I can write. Stop share. So what is the thing on the cache line? Let me just go to an empty page. Okay, here, I'm just in this page. When you have a cache line, you're gonna have a tag. Well, let me change this important. You're gonna have a valid bit, but you need a bit that is dirty to know, did I do a store? Whenever you do a store, you modify the dirty bit. So the bits that you have per tag entry is the number of bits that you have here on the tag. In the question where I forgot, but it was 34 minus 14, I think it was 32 minus 14, and then you have plus 1 plus 1, 1 for dirty, 1 for valid. There are a lot of questions about how many quizzes are considered. Remember, the more quizzes that we do, the more that we drop. Now, the reason why it's 512 is you have, I think it was a 32 kilobyte page, a 32 kilobyte cache, and then you have a cache line that it was 64, and that's 512. The associativity doesn't change the number of cache lines that you have on the system. It's only how do you organize. For every cache line, you need one tag. So the associativity does not change the number of tags that you're going to have in total. It's how many do you check in parallel, but it doesn't change. Now the 14 is for the, so the, when you get the address, you have an offset, you have an index, and you have a tag. So what we were trying to do is to compute the size of the tag. Now the index, it will increase by 1 bit when I have a two-way associative. It will increase by another bit when I have a four-way associative. And that's the reason why it's one extra bit that you need on the tag. So for the number of number of tags, the associativity doesn't matter. For the number of bits on the tag, the associativity matters. Yes, the number of indexes is 2 to the 14. So that was for the quiz. So let me continue with the lecture because I want to go over the multiprocessor. So the TLB is the issue is that I have been mentioned before, the operating system support 4 kilobyte pages, but to have only 4 kilobyte pages is not great. If you think about it, if we have a 64 entry TLB, it maps only to around 256 kilobytes. And this is much smaller than most of the L2 and L3 caches, which means that the TLB miss will be happening very frequently. The solution for this is two options. One is to do super pages, to do like a 4K, but also to support like bigger pages like 1 megabyte, or the typical one to have a small TLB and then you have a big TLB that if you have a miss on this TLB, you will check the large TLB. Both solutions are implemented in current systems. What are the trade-offs? Why not everybody using larger pages? So usually larger pages, the issue is that they have more memory fragmentation. You lose more memory. For historical reasons, memory was more precious in the past, like cost per byte, which means that we have, now if we were designing the system, we'll have bigger pages. but all the software has been designed with smaller pages. But if you look back in the history, in the 70s, most of the pages used to be 512 bytes. Then in the 80s, they're starting from 4K. Some people were started to have longer pages in the 90s, but these larger pages is only when you have super pages. Because of software reasons, all the systems that I know support 4K pages. Because there is a lot of software that it will work only with 4K. We're not going to go over the details, but I put the slides of how is the translation from virtual to physical on the RISC-V. In RISC-V, they have several versions of virtual to physical. They have the SV39 that translates from 64 from this. Do you see that's the translate 39 virtual address to 49. Well, so this is 39. This is 0 to 39, so 50 bits physical address. Notice that neither of them is 64-bit. Not even the virtual address is fully 64-bit. Now, which means that in the register, you might have a 64-bit from 0 to 63. But here it's telling me that it reaches only up to 38. So what happens with those bits? On the ISA, they say that to be correct, use a SV39. If here you have a 1, you have to sign extend everything. So it means that you can create an illegal pointer, and then when you try to access, so if I put a 0 here, if I access with this, there will be a illegal memory access permission, and the operating system will terminate your application. So those addresses are supposed to be sign extended, those bits. So this is for the virtual. The physical has less, and we already went over that before, because there is no point of having even so many bits of memory. You are not going to buy terabytes and terabytes of memory in your machine. One thing is interesting is that the RISC-V had 2 modes. Maybe you need applications that require more memory, so they have the SV48 too. The SV48 adds another layer of indirection. Notice that there is 1, 2, 3, 4 on the page walk. This one does 1, 2, 3, 3 indexes on the page walk. So it's a little bit, when you have a TLB miss, the SV48 will do 1 extra load on the page walk. So it might be a little more inefficient. So this is the topic for TLBs and virtual memory. Now we're switching to multiprocessors. Any question on, okay, what's internal fragmentation? So what internal fragmentation is that when you have you might have your, let's say, 1 gigabyte of memory. If you have the pages, you're gonna do malloc, and you will have here 4K, and you will do maybe malloc of 3 kilobytes. So you will do 1 page here. But what happened if I did 3 kilobytes? Here there is 1 kilobyte that I don't have protection. If you use something like Android, every time that you do a malloc, they try to separate. And the reason is that they try to separate is for having a little bit of memory protection. So you are going to be wasting, if I did 3 kilobytes, you're going to be wasting 1 kilobyte of memory. That's what's memory fragmentation. That you can, for security reasons, every time that you do a malloc, it translates internal inside of the operating system to something SBRK, a different code. But you might want to have different chunks of memory separated, so that if the application goes out of the pointer boundaries, it doesn't fail. But in order to do that, you're going to be wasting a little space. How much are you going to be wasting? Well, if you have a 4 kilobyte page, on average you're going to be wasting half a page. So the bigger your page, the more that you're going to waste. So that's what's internal memory fragmentation. Any other question? No? So let's have a 1 minute mini break and we are switching to multiprocessors. Well, that's main memory. Well, main memory and then multiprocessors. This is just very fast thing. Well, someone is asking, how exactly can I test on TLB? Well, I'm not going to tell you exactly how I can test, but things that I can ask is, if you have a virtual index cache, do you need to flash the cache on context switch? Yes or no? Or I can put you a cache size and then say, can you build a virtual index physically check cache? Yes or no? And if not, what's the reason? And I can explain several reasons and one is correct. So it's mostly that type of question. Or I can even have a TLB that I do several accesses and then you have to tell me, is the question, is a TLB hit or is a TLB miss? You can even do a page walk. So you have this translation and you have 3 indirections. How many loads does the page walk do? So there are several type of questions that you can have on the TLB. One thing that we are having on these slides is memory subsystem. This I'm not gonna ask any question, and because they canceled the last class, I'm gonna advance fast. But the main idea here is that I just wanted you to have a little bit the idea, the names, so that when you talk, is that when you have a miss from the caches, you're gonna go to something called memory controller, and then you're gonna go to the DIMMs or DDR on memory. They have some organization inside, but the reason why this is a totally different technology is because it's a capacitor. In fact, what you build is a little capacitor and you check what's the charge on those capacitors. And because those capacitors lose charge, that's why it's called dynamic memory. And if you power down your computer, the memory is gone. This is a little bit more details SRAM, DRAM that I'm gonna skip this quarter because there is no way to ask a question and let's go over the multiprocessors, it's more important. So why do we care about multiprocessors? We care about multiprocessors because they are everywhere. 20 years ago, there were not multiprocessors everywhere. Now we have them because of the power wall. As the processors have reached the limiting power, we have been adding more and more processors in order to increase the efficiency of the system. Now, from a very high level picture, what's a multiprocessor? So you are going to have a processor, a CPU, that is what we have been seeing up to now. You're going to have several CPUs that they're going to share a memory subsystem and all of them connect to the same memory. They're able to see memory across them. Now they're also going to share the I/O. So you have a PCI or UART. Every CPU can see the memory. In a way, you can think that there are copies. You have many copies of the same core inside the same system. Now, what's the difference between a multi-core and a multiprocessor? So in the past, everything was multiprocessors. So in a multiprocessor, you have one chip, and then you were having another chip, and here you have a core 0, and here core 1. So multiprocessor implies that you have multiple chips. Okay. The multi-core is do you have one chip and you have several cores on the same chip. So as you can see, it's a very small difference, but you will nowadays more people tend to have multi-cores for sure. Some do multiprocessors. Multiprocessors tend to be more a server thing. Multi-core, it tends to be more like what you have in your desktop or what you have in your phone. Now, what is the idea of parallel computing? You can divide your problem into sub-problems, and then you can solve all those problems in parallel. Now, the usual problem that you're going to have is sizing, and questions that you're going to have to address is how many cores do I have? How powerful is each core? How much memory can I have in total? But the main important is how many cores, and then how is the data shared across the cores. If your application requires to share a lot of data, it's going to be slow. If your application is able to partition the data and then they work separately and at the end they just produce the results, then more likely works in the parallelism. And this is going to affect your system, the performance scalability. After all, you do parallel system because you want to go faster. So how do you measure performance in a parallel system? So you are going to have the speed up or the piece for parallel. And this, what is speed up? Time old divided by time new. So time of the sequential application divided by the time on the parallel application. Time old versus time new. Now, how is it going to look? So if I have 1, 1, here is my time for my sequential application at the 1, 1. Ideally, what you want, and I'm going to do it in green, what you want to do is something like this. Why are you going to want this? Because if I have something like 4 cores, this is the number of cores. This is going to be the time, the speed up parallel. So you are going to want to have a 4, which means that if I go to 4 cores, I have a speed up of 4. It means that the time parallel is 1/4 of the sequential. That's your ideal. The little trick is that usually you don't start there, you start around here. Why do you start lower? It's because when you parallelize your application, it's not going to be as efficient as the sequential application. So you start with a slower system when you start with 1 core. And ideally, what you want to do is to do something like that. It starts to grow, and then there's going to be a time when it's going to go down. So you're going to design your application, or depending on the problem, it gets automatic, that you are going to have enough data to do things in parallel, but there is a moment in which there is more cores than data, and they start to talk too much. And then you keep adding cores to the problem, it gets even slower because they just keep talking and not doing anything. In a way, it's like a little bit like people. If you want to solve a problem, sometimes it's easier just to do it with 1 person, 2 or 3. If you put thousands of people to solve the same problem and they have to talk about it, it's going to take more time to talk about it than to solve it. So that's what tends to happen in the applications. That's what you wish. The reality is that many times you tend to do this thing. So, oops, that's a horrible color. You start from a low point and you keep going slower and slower. This is what tends to happen whenever you start to parallelize an application. Because you do something and it doesn't work. As you have more experience, you hope to go towards this case. So measuring the performance, you can have the speed up that we have computed here, or you can have the efficiency. So what is the efficiency? Is how efficiently I'm parallelizing the application. So I have my speed up in parallel divided by the number of cores. This is the number of cores. So if I were doing the plot, ideally, so if I do the green again, you will want to have a very high efficiency. So let's say 100% or 1 efficiency. So you will want to have that efficiency as I increase the number of cores. The reality is that it's going to be something going down. As you add more cores, the efficiency is going to go down. Now, the parallelizing from a hardware point of view, it's only about caches. If you have a multi-core, the main change that you have to do is how do you make the caches work? Once the caches work, the problem is solved. And the reason why you have to make the caches work is because you have to share data across applications. And the caches, in a way, they bring the data local to your application. Yeah, so someone is asking the TP is time parallel. So let me show you what's the problem if I don't do anything. If I have a normal CPU and I have 3 cores and I have 3 caches and then I have a memory and here I have an L2. What's going to happen on this sequence? First I'm going to do this load, then the store, then this load. TSEC is time sequential, the non-parallel application. I see that someone is asking online. Now, what is going to be the sequence? So the first thing, I'm going to do the load. Now it's going to be a cache miss because the data is not there. So the second thing, I'm going to go here. The third thing, I'm going to have a copy here. I'm going to put a valid bit and the tag is 400 and some data. And then it replies to the CPU. Now, after this other core is going to do a store. So what it's going to do? It's going to go here first. It's going to be a cache miss. Then it's going to go down. Why it's going to go down? Because even if it's store, it has to bring the cache line to have valid 30, 100. So this is going to be the 3, and then it's going to be modifying some data there. So stores trigger a cache miss. So the 30 you set it once the cache line comes after 3. You put the 30 bit as you fill the cache line, and then you service the processor 4. Now after that, so this is the first thing, this was the second thing, and then you have the third core. What is going to happen with this core? And this one is when we are going to see the problem, because up to now everything was working. So when I send the load, I'm going to have a cache miss. I'm going to do the same. I'm going to memory. Now when I come back, what do? I set my valid bit, my dirt is clear, I have my tag 100, but the value, if here I have the value, let's say A, here I overwrote it with a B, here I'm going to have the value of A. Because this B, I don't see it didn't go to memory. So this processor, this load, doesn't see the last store on the system. If you think about it, there are 3 copies on the cache line on the system. So we have 1 copy, 2 copies, 3 copies, but we have 2 different values. We have A in these 2 CPUs, but this one, it did a store, it has a value of B. So the data is incoherent or inconsistent across the CPUs. I will use the word incoherent for this. This is the reason why the caches don't work, and that's what you have to fix. So let's see if there is any question. If you have a write-through, if you were having a write-through caches, if you give a space between the loads and the stores, that will solve it in this case. But if you have many stores, it will not necessarily solve it, and there can be race conditions. So you still have problems with a write-through, but it will make this case less frequent if you have a write-through. That was a good question. I'm not so sure what is the second part question that I see on the chat on Zoom. This didn't happen at the same time. This one happened first. Many cycles later, the store happens. Many cycles later, the load happens. As you start to interleave the thing closer, more strange things can happen. But even if they are not happening at the same time, you have this problem. And it's easier to understand, because when you put many things at a close time, it gets more complicated. So conceptually, you did all the transactions in red first, then all the transactions in bluish first, and then all transactions in green after. So how do we solve this thing? So there is a question about what is parallel sequential. So here in this example, I have 3 cores. So each one of them has his own PC or program counter. So they are going to be executing instructions by themselves. It's going to be PC plus 4, PC plus 4, PC plus 4. And each one of them is going to be doing PC plus 4. There is no coordination across them unless you add loads and stores to synchronize. So because they have 3 CPUs that each one of them is running their own PC and is totally independent, we have a parallel system. In this case, it's a 3-core parallel system. What is the parallel? Is that we have 3 cores doing their own things. You're going to have, if you run in one of them a chess game, in the other one your video encoder, that works fine and there is no problem. The issue is going to be that when you try to parallelize an application, usually you give a chunk of a problem to one core, another chunk of the problem to the core, and then they have to synchronize or communicate. Here they were communicating because all of them were using address 100. If they were using totally different addresses, then the system works. When they start to share addresses and they want to communicate, is when you have a problem. And if we think about the virtual physical address, let's assume that all those guys have physical addresses, because otherwise will be a problem too. So is any other question? So the MS, so the course, there is no downgrading performance to interact or anything like that. If the loads and stores, if we are having the system that we have here, if the loads and stores happen, they are not going to affect each other. The only way that they will affect each other in performance is that when this one sends a request, maybe this other core is sending also a request. They are going to compete for the memory subsystem, so there's going to be competition for some resource. But if they were hitting on the L1 cache all the time, there is no big competition and it should be super fast, as long as you don't have power consumption competition. So unless they don't compete for a resource, they have a structural hazard, they don't slow down each other. Any other question? No? Okay. So what is the basic paper? This is a paper for 1982. You think about it, is a paper who solved the parallel processing, and it's not so old. 1982 is just 40 years old. So computer architecture is fairly new field. So what is the basic protocol? That it works, but it's not going to be the best. One thing to remember is we have 10 minutes and then we start the quiz. So if I forget because I keep going, stop me so that we do the quiz. Start in 10 minutes. So what is the basic protocol that we have here? We have MSI. MSI starts from modify, share, invalid. In the past, every tag was having a valid and a dirty bit. Now we're gonna get rid of these things and we are gonna have an MSI. So it means that the cache line can be on M state, or it can be on S state, or it can be on invalid state. After you reset or some conditions, it can be an invalid. So it can be in one of the three conditions. So the states can be invalid, share, or modify or dirty. So we no longer have the valid and dirty bit if you have this coherent support. Now the processor is going to be doing or read or writes, or another way to see this one is going to be doing loads and stores. But we are going to have the core 0, core 1. So we're going to have a cache. They always have the private L1 cache. And then we are going to have a bus or the lower level. So this cache is going to see requests from two sides. From this side, it's going to be seeing the load stores. From this side, it's going to be seeing those requests. It's going to be seeing a bus read or bus read exclusive or write back. So the cache is a state machine that is going to be looking at requests from the core or going to be requests from the bus. So what is the thing that you're going to have on the MSI protocol? For every cache line, you have the three possible states, I or S or M. So you have many cache lines. Each one of them is going to be maybe this one S, this one in M, this one in S, this one in I. Every cache line is going to have a different state. After you reset the machine, all of them are invalid. Now what happens? So we're going to build a state machine for the load. What happens if we see a load? If we see a load, we're going to put the cache line in share state or share. So if we see a load, we do share. But what do we send on the bus? We send a bus read. When we see this load, we're going to send here a bus read. It's the cache miss. But the cache miss is going to have we're going to have sending down three type of message. We're going to send it a bus read or bus read exclusive. Bus read means give me a line, I don't need to be the only one. Bus read exclusive means give me the line, I want to be the only one. So if the cache line is in share, if I do another load, I have a cache hit. I don't need to send a bus read because I already have it. So it's a cache hit. Now, if I'm in invalid and I see a store, what I need to send is a bus read exclusive. So I'm going to say I want to be the only one. So I'm going to go to exclusive. Now, similarly, if I'm in exclusive or modify and I do a store, I don't need to do anything because I already have the line in modify. It's already a cache line that I have dirty and I'm the only one having a copies and in modify state. If I'm in share state and I have a store, I still have to send a bus read exclusive. And this one is interesting because before, this in fact is the key state that there is a change. Here the line is in share. I still have a cache hit if I do a store. But when we are sending a load, we are staying on the same state. But if we send a store, we are going to have transition to modify. But in order to go to modify, we have to send the bus read exclusive out because we want to be the only one. Which this brings us to, from each one of those states, you have to look at the transactions on the bus. If I'm in a shared state and I see a bus read, I will stay on the same state. But if I see a, byte read exclusive, I'm gonna go to invalid state. Now here is optional. I can do a write back. Now if I'm in the modify state, let me change the color. And if I see a byte read, no, byte read exclusive, you're gonna have to do a write back. Notice that here I'm saying optional write back or not. So if I'm in modify state, for sure I have to go to invalid because only one can have the copy, and for sure I have to do the write back because I have the data modified. But if I'm in share state, I have a copy, I have to go to invalid because no one else can have a copy, but I can send the data or not, that's optional. The reason usually you give an acknowledge, this is like more like hack, I have data. And the reason why you might acknowledge that and you have the data is because it might be faster to transfer from cache to cache than going to memory. But the protocol can work with this write back or without. So what you have to do to fill this state is to look at every possible message. So if I'm in share, I can see a load. So if I get the pointer. So if, for example, if I'm in share, if I see a load, I stay here. If I see a store, I go there. If I see a byte read exclusive, I go there. There is one missing, is what happens if I see a byte read. If I see a byte read, oops, wrong color. If I see a byte read, I'm staying on the same state, and again, oops. Optionally, I can do a write back. Now, here I see a byte read. So if I see a byte read, I have to do a write back. But notice that if I see a byte read, I'll switch to share. If I see a byte read exclusive, I go to invalid. So if you do this diagram, this transition in a cache, you solve the problem for the cache coherence. It's not going to be the best, and we're going to see the changes. But if I do here the transition, let me do this, and then we're going to see how it behaves, and then we're going to do the quiz. So what is going to be the sequence? When this one does a load, we're going to send the request. So we're going to send first the load. The second, it was a cache miss, so we're going to send a byte read. So when the data comes back, so this one is going to be to share state. Now what's going to be happening when we do the store? So it's going to be 4, we're going to have a store. So this one is going to send a byte read exclusive. Now, because it's a byte read exclusive, you can think that this cache is looking at the bus, and it sees the byte read exclusive. Because it's a byte read exclusive, it will have to, at 6, it will do a write back optional. That's the part is optional, but for sure from here we'll transition to invalid because it's a byte read exclusive. So when the data comes back, here the line is going to be on M state. Now the value here was A. This is going to be changing to B, but this copy is already gone because it's gone to invalid. Now when this one does the next step, 6, 7, 8, it's going to do the load. So this is gonna trigger a pass read 9. So what is gonna be forcing this guy to do? At 10, it's gonna force it to do a write back, and then it transitions to share. Now this data we did the write back goes here. So here it goes the share, and it copies the B because it did the write back, and here we have the value of B. Now we don't have an inconsistent state as we were having. So let's stop here. So it's time for doing the quiz. The quiz is not collaborative. Let me reply on the quiz individual. Quiz not collaborative. Quiz not only homeworks. Okay, I don't know my okay. So the quiz are not collaborative. So only the homeworks you can collaborate. The quiz you are supposed to do by yourself. So I'm gonna stop talking, but the idea is that you go to the quiz. It's open now by time, and you can do the quiz. I'm gonna stop talking, and that's the end of the class. So I'll post the recording of the video, and at 4 or 3:30 I'll check, and we'll have office hours later. You want to connect? Any question before? No? Okay. So enjoy the quiz.